for this case is given to us by tensile test, for example. So one direction. This over here is from what? Combined what? Loading. Combined loading, i.e. we have normal stress, or we have shear stress, and we have normal stress. So the only way to relate this, okay, I'm going to show you how we're going to relate this. So from here, I'm going to copy the element. Right. So by looking at the element, okay, we are going to draw Mohs circle. Okay, for this case, 3D Mohs circle. I repeat again, we're going to draw. No, let's not do 3D. Okay, let's do 2D first. Okay, I don't want to overwhelm any of you. Okay, so we have our axis over here. Right. So we have our normal stress, and then we have our shearing stress. Okay. So the shearing stress element rotate clockwise, element rotate anti-clockwise. Okay. So if I have to sketch the stress X line, this is where our stress X line is. So it's in tensile. Okay. So this is our stress X. Okay. Then we have our stress Y, right? Sorry, stress Z. Beg your pardon. Right. This is our stress Z. Okay. And stress Z is equal to 0, as you can see. Right. Stress Z is equal to what? It's equal to 0 megapascal. Right. Then we also have a what? We also have a shear. So this is our shear. We have our shear. Right. So the shear, we have to draw the positive and negative shear. Right. Positive and negative shear does not mean anything on Mohs circle. Okay. Right. So the shear is dependent on the rotation of the element. Okay. So if I will call this surface X, or point X on Mohs circle, and point Z on Mohs circle, right? If we put our finger down here, and due to this shear stress, is going to generate a what? A clockwise rotation. Okay. So stress X, right? This is our shear. Okay, I'll write this at this point. This is our shear XY, and this is also our shear XY. And we know, no, XY, XZ, I do beg your pardon. Okay, and we know that shear XZ is equal to shear ZX. Okay. So from here, point X, the element is going to rotate in a clockwise direction. So we write down here that this is point X. And at point Z, all right, if you put your finger at the center over here, the element will rotate at an anti-clockwise direction. So over here, this is your point Y. So we are going to construct a line. And then from here, we are going to draw a Mohs circle. So now we are constructing a mole circle now. Okay, so this is our mole circle. Right. So what this mole circle have in common, if you have this point over here, so I'm going to call this stress 1 allowable. And over here, this is our stress 2 allowable. Right? So what you realize regarding stress 1 allowable, okay, what we realize about stress 1 allowable and stress 2 allowable is that these points are known as the principal stresses. So i.e. shear stress is equal to what? 0. So therefore, the factor of safety will be equal to stress yield divided by what? Stress 1 allowable. So over here, this is from materials handbook, right? Materials handbook are basically data from this table, as you can see over here. So now we can relate them, right? The allowable is basically this point over here. The shear stress is equal to 0, right? For the yield from the materials handbook, right? If we look at in tensile, the yield, right? In tensile, the yield, this 250 is taken when with a what? The yield, this 250 is taken when the shear stress is equal to 0 at the principal point, right? At this point over here, right? At this point over here, them circle in orange, the shear stress is equal to 0. Okay, so therefore, in order to determine the factor of safety, right, you have to draw what? You have to relate with what? Mole circle, right? Because at this point over here, like this point X and this point Z, I do apologize, this is Z, right? This point X and point Z, as you can see down here, it belongs to the element, but we can rotate in such a way, right, that the shear, the allowable over here, the shear stress is equal to 0. Okay, so we have to use over here at the top is also the principal stress from experiment. Okay, then we divide by principal stress from mole circle, right? Then you can determine the factor of safety. Why we have to do that? Because in the material handbook, as you can see, the testing are done either in tension, either in compression, or either in shear. They don't do it in what? Two direction. They only do it in unidirection. So in order for us to relate our structure that is not unidirection, so this is two direction, right? You have normal stress and your shearing stress. You have to apply what? You have to apply mole circle to determine principal stresses. After knowing your principal stresses, okay, then you can formulate your factor of safety. Okay, so that's why not next week, the following next week basically, okay, we have to learn what Mohs circle. Then we can pick materials from the materials handbook. When I finished my undergrad degree, I did not know this at all. Okay. When I started working Rolls Royce, I just said, the shear stress is so little, let it be equal to 0. Okay. Then when I actually do the design, I just put a higher factor of safety. Right. So that is not a good practice at all. Okay. Right. So now let's focus on this problem over here. Okay. What we're going to do is we're going to determine the norm. We are going to determine a few things. Okay. We are going to determine the axial force, the shear force, and the bending moment acting on this structure, and then how we relate to the element. Okay. So this is a bit of a revision, okay, for Thursday term test also. So let's look at this example. So what we're going to do, the first part, basically we have done it before. I've taught you guys before, okay. But let's try again. Okay, so we are going to determine the principal stresses, maximum stresses at point A, and we are also going to do point B. Okay. Now let's look at some theories first. Okay, let's look at what formula that we are going to use. Okay, so we know to calculate the normal stresses. Right, so we are going to calculate the normal stress in the z direction. It's basically equal to plus minus pz over a plus minus my over iyy multiplied by distance of x plus minus mx over ixx at a distance y. Okay, so we are going to use this equation, right? So this we know, right? This should be very familiar to you guys. This is due to the axial load. And this equation over here, both of them are due to bending moment. Okay. This is just the normal stress. We know that the structure is under shearing stress also because the formula for shearing stress. Okay, so the shear xy is equal to the shear yx, and this will be equal to torque in the z direction over j multiplied by a distance y or distance c plus minus of vy over ixx qx over t plus minus by vy or vx over iyy qy over t. Okay, and over here this is due to the torque, and over here this is due to the shearing force. Okay, let's take a 5 minutes break now. We come back at 8:05.